All right, welcome back to another installment of AP Chemistry from my kitchen. Well, we are taking a look today at another instrument, and it's an instrument that we've seen before. And now that we have learned a little bit about organic molecules and we've learned a little bit about isomers, we can revisit it to see what some of its better uses are for. That magical instrument that I'm talking about is one that we saw in the beginning of the year, and it's called the mass spectrometer. So back in the beginning of the year, we were using the mass spectrometer. If you don't remember what I'm talking about, it was that hockey stick or sock looking instrument that we were drawing. And we were using the mass spectrometer to figure out weighted averages. So this periodic table behind me here, we know when you look down at the bottom of the elements, things like carbon are 12.01 and oxygen is 16.00 and chlorine is 35.45, stuff like that. And we know that protons weigh 1, neutrons weigh 1. So where's that decimal coming from? How does 1 and 1 equal, 2.5 or something like that? So, and we know that that's actually because of isotopes and averages, and we were able to find what these isotopes were and their abundances using the mass spectrometer. But it could do so much more for us. The mass spectrometer could be used to help us distinguish between isomers and different organic molecules as well. So let's take a quick look back over at the mass spectrometer again and be reminded a little bit of what was going on there. So when we're looking here, the mass spectrometer, what we were using in the past is this concept of finding the relative molecular mass. We were basically finding our periodic table masses, and we were using percentages that were showing up. And we were also able to use a mass spectrometer to tell us exactly how heavy something was. And so it allowed us to go from empirical formulas to the molecular formulas. So you'll remember the empirical formula, percent to mass, mass to mole, divide by small, all that stuff. And then you would be able to compare that to the real molar mass over here. And well, now today what we're going to look at is see if we could use it to help figure out some organics. So let's take a quick look at the instrument itself again. I drew this ahead of time to try and speed this video along a little bit for you guys, but you should recognize this. And so I just want to walk you through the steps real quick again. And the idea is you are taking a look right now at the different steps. Remember that the first step that we had right here was vaporization. You were to take a chemical and you had to get it into its gas state so that it would free to separate and move throughout the thing. A solid's not going to travel through this very easily. So that was our first step, was to vaporize it. The second step that we see right here was the ionization step. And we bombard our substance with electrons. It's basically a bit like a waterfall of electrons. And so as that carbon moves forward, eventually it gets into that stream of electrons. And what we see is right here, one of those electrons that's traveling like a waterfall, it smashes into our carbon atom and it knocks off an electron. Just like in a bowling alley, you throw a bowling ball, it's going to hit those pins and knock them everywhere. Same way. And so we can see right here, our carbon is now missing an electron and it's got a positive charge. This was very important because it allows step 3 to occur. Once we have an ion, it can interact with an electric field. And so these two plates right here turn on and it causes my positive to move forward. It's going to be attracted to the negative plate right here, and it's going to be repelled from the positive plate, which gives it forward motion. It shoots it forward. Now, once this positive charge is moving, any moving electric charge creates a magnetic field. And that's what step 4 is all about. We have a north pole and a south pole right here. And so that is going to cause my moving charge to be attracted toward one and repelled from another. So if my charge is very, very light, it's going to be deflected a lot, and we end up hitting over here in our fifth step, which is detection. And then if it's really, really heavy, it's going to barely bend, and it's going to strike somewhere over here. Now, how does this apply? This is easy to see how it works with just individual atoms. You know that the light atoms are going to hit down here, or excuse me, the heavy atoms are going to hit down here, and the light ones are going to hit up here. But how does that work with a molecule? Well, it all goes back to step 2 right here. Step 2, when you create the ion, when you're working with an organic molecule, it starts out as neutral, and that waterfall of electrons has some options. It can strike electrons located throughout my molecule here. It can hit anywhere. And when you picture these bonds, you basically have electrons that are here and here in the bond. You have them here and here in the bond. And basically what's going to happen is it's going to come in and it might hit right there. So what does that mean? It means that this bond breaks and this electron flies off. And so now this particle right here can move through the mass spectrometer. This one cannot, because it still has its electron. It has not turned into an ion, so it cannot go through step 3. There's no charge for it to be accelerated. So if we think about that, this guy over here is going to move all the way through, and when it strikes the detector, how heavy is it going to be? Well, the carbon weighs 12, this weighs 1, 1, and 1. We would expect 12, 13, 14, 15. We would expect a mass of 15 to pop up on the screen. So we see that where this breaks, it's going to start giving us clues as to what our molecule might be composed of. So let's take a quick look at an actual spectrograph. So we see 2 readouts here, and these are isomers, pentanone and pentanone, right? We know that if we were to draw these things out, the only difference between them is a location. These are positional isomers. So if we were to draw them, it would look like this, right? So this would be, the first one is 2 pentanone. So this one's 2 pentanone. We could see that ONE bond, the ketone on number 2. And then the next one is 3. We can see that it's located on 3. So you'll notice that when we look at these graphs, they have some different peaks. They have some different readouts that are appearing here. So we've got some little ones down in here, but the major peaks that are showing up, we see them right here. Now you'll notice when you look at this, 2 of them match perfect right off the bat, 86. Well, what you find is that way off the very last peak that ever forms, this guy right over here on both of them, this is the molecule full-sized. It's like when we were breaking this thing apart up in here, when this guy was getting broken, it didn't smash an electron out of the middle and send just half of it through. It's knocking something off of a corner or an inner electron. It's turning it into an ion somehow, but it's just barely grazing off of the edge over here. And so it's actually not fragmenting it. This is the true mass of my unbroken substance. So if you just add up this right here, the real molar mass of this structure should be 86. So that's not a really helpful peak, because both of them, being isomers, have the same exact mass. So those I'm going to kind of ignore here. They're not going to help me. I've got to get to these other peaks. And so what I want to start doing is looking at my structures and saying, where could they break? You know, what are some options where they break that might help me distinguish between them. So let's say, for example, that the electron wave came in and it smashed this one off. And this little piece right here flies through, and this piece flies through. We just said in the previous example, carbon is 12 plus 3 hydrogens is 15. Well, this one's 15. Is that a very useful peak to me? And I would argue that it's not useful, right? A CH3 can pop off from right here. We can get one breaking off over here. We could get one breaking off over here, right? They pop up all over the place. That's not a very useful fragmentation pattern. So that's not one that I want to focus on. I want to try and say, okay, if I broke this, where would it be kind of unique, right? So if I was to break it right here, let's say, right? So maybe the electron came in and it smashed it off, and this got the positive charge right there. What would this weigh when it moved through and it hit the detector plate? And could this molecule down here give me that same mass? So if I add this up, we go carbon is 12 and 12, so we've got 24 and 16. Okay, and then we've got 3 hydrogens. What are we at here? This is 43. All right, I think so, 43. Yes, 43. All right, so then let's say we try and break it down here. Maybe we'll have it come in just like how we had it come to the side of the carbonyl, and we'll smash it off right here. And so maybe this piece right here gets a positive charge. Okay, so we've got, let's see, 12 times 3 is 36, 40, 41, and 16, 57. So what I'm doing is, in my head, I'm just adding up the carbons. So carbon, 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 oxygen, and then hydrogen, 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 hydrogen. And all that, if you add it up, is about 57. So that's not a match. I don't think this one up here could give me a 57 if I tried to add this side. So what if my electron went in and it hit over here, and this was the positive, right? That would fly through. So 12 times 3 is 36, 37, 38, 39, 40, 41, 42, 43. So this one would weigh 43, which is the same as this 43. So I'm expecting 43 to be pretty popular over here. And then maybe this fragment here, this one would be, let's see, 24, 25, 26, 27, 28, 29. This one would be 29. So let's just see if we could detect any of these peaks. 43s, 29s, 57s. And so if we start looking up here, you'll notice what we see right there. I see a 43, I see a 29, I see a 57. So we start getting an idea. Okay, so I don't know what's in my beaker. What isotope did I make, or what isomer I mean? We run it through. 43, looks like this one is the 2-pent. And this one must be the 3. Okay. Let's try some other examples. Let's try another one. Empirical formula is C2H6O. C2H6O. So when I go to do this, we take a look here, and the biggest peak I see is 46. So this is the real molar mass right there. That's what the real molecule weighs. That's how heavy it truly is. And I'm not sure that, what do we got? 2 times 12 plus 16 is 40, and then 6 more is 46. Okay, so it looks like the empirical formula is also my molecular formula, right? They match up. So this was equal to 46. This is equal to 46, so that's good. So it's reduced as far as it'll go, but it's also what it really looks like. So the 46 is not super helpful to me. Let's go ahead and draw out some structures. What could this look like? C2H6O. So if we are doing this, the first way that I would do it is C2H6O. So most people draw it with the alcohol. Okay? So if we were going to do this with the alcohol, what kind of peaks might we see? So I might see something here. So that's about 17. I might see something like, so, or it could go to this side, right? It could smack and put the plus here. And so that would add up to 29. What else could it have done? So I could see for this one a 17. I could see a 29. Any other combos that I could get from that? Let's see. Maybe we can go this way, right? So we've got this side here. So that'd be 12, 13, 14, 15. Or this side over here, we would have, what does this add up to be? So 16, 17, 18, 19, and 12 is 31. So these are some possible peaks that I would have if it was an alcohol. What's the other way that I could have drawn this? Well, I could have just put the oxygen in the center, and this could be a different isomer that we get. So what are some different things I could get? Well, I could split it here and get 12, 13, 14, 15. Or maybe this side gets the positive charge. And so we would see, what would we see for this one? This would be 31, 16. Yeah, 31 for that one. Are there any other ways I could split it? It doesn't look like it. Because if I come in this direction here, I'm just creating one that I've already done. So this would look like 15 or 31. So we've got 15, 31. Those are also here up above. So we see some similar peaks. So if I only see 15s and 31s, it's probably this one. If I see some additional peaks, then it must be this one. So let's take a look. And we've got the 15s. There's the 31s, but I also see a 29, which the only one that could give me a 29 is this one. So this must be, if we're going to name this would be 1, 2. So we've got ethanol, and it's always going to be on the number 1. So you could put the number 1 if you want, or it's not really necessary, but this is going to be the alcohol. So these are a little bit more complicated to read, but not impossible, as long as you just start chopping pieces off and seeing how heavy it is. I mean, technically you could chop a hydrogen off if you want as well, and that's what we actually see happening here, right? It's at 45, it's just lost a hydrogen or something like that. But that's not usually very helpful if you just lose a hydrogen, so I wasn't adding any of those. All right, so I'm gonna post the assignment, give it a try, start trying to cut things in half, and hopefully you guys will do okay with this, but let me know if you're struggling. Talk to you later.